step is differentiate f of x, i.e. obtain first derivative of x. Obtain that. Number three, substitute xn in f of x and f of xn and f derivative of x, so as to find f of xn and the f derivative of xn. Then number four, use the formula xn plus 1 equals to x that plus over the first derivative of this, which is the Newton-Raphson formula. So how do you use this? So what you do here is you now substitute your f of xn, which you obtain this step, and then obtain this as well, and this one will be now the Newton-Raphson formula for finding the root. So this is all about the derivations of this. Later we are going to talk about how do you use the formula to find the root with example. So the examples I'm giving for examples for derivations. Example number 1, derive the Newton-Raphson formula for finding the roots of the following equations. Derive the Newton-Raphson formula for finding the roots of the following equations. Part A, x cubed plus x minus 1 is equal to 0. Part B, exponent x plus x minus 1 equals to 0. Part C, sine of x is equal to 2 cos of x. Part D, x minus 2 sine of x equals to 0. Part D, sine of x equals to sine of x is equal to x. This is example number 1, A, B, C, D. Example number 2, part A, we are going to now derive the expression for x cubed equals to 2. Part B, we are going to have x equals to 1 out of, say, n, and so forth. So other examples are following. So let us, in the meantime, work out some few examples here. Then we see what next. Okay. So what we are going to do is, to candidates, when you are attempting a question and the first thing to do is to derive, what you do here is first understand which function are you dealing with. This is a polynomial function. So what you do, you let f of x to be equivalent to x cubed plus x minus 1. Remember, we said the function should be of this form first. That means all the variables are supposed to be on the left hand side, or any term which is not 0 must come to the left hand. That is the best way you can always have the, because you are looking for where the root, where the function cuts or the curve cuts the y at the x-axis. Now after having the function, the first step was that. The second step was differentiate this function, and this will be 3x plus 1. Why is this 3? We say in differentiation we drop the power and reduce by 1. That is how we differentiate the polynomial function. So this is x power 3. When I drop a 3, it is a 3. Write x power 3 minus 1 is a 2. Then plus, when I differentiate x, I get a 1. Then when I differentiate a constant, I get a 0. Then we substitute xn. This is where there is x, we now put xn. This will be xn cubed plus xn minus 1. The same, also substitute xn where there is x. This is 3xn squared plus 1. Now, examiners have no marker for this. The marker is always given when you differentiate the function, and then this substitution, because someone can do this in the formula like we are going to say. So after you achieving all this, you now quote the formula which says xn plus 1 is given by xn minus f of xn over further derivative of xn. What is next is now to substitute. So this implies that xn plus 1 is going to be xn minus, remember this negative simply subtracts all these terms. So don't always be misguided on how you substitute. So this one we put f of xn, it is here. This one is also here. So when I put equation star, f of xn is what is going to be here, and that is xn cubed plus xn minus 1 over, now we put the further derivative, that will be 3 xn squared plus 1. Now this is the Newton-Raphson formula for calculating the root of the equation. So when you are asked to derive, this is where we have. But to mathematicians, you can always simplify. So when I simplify this, I can have the LCM taken. So you need to be very, very careful when you are dealing with the fractions. So our xn plus 1 is going to be LCM. Remember here something is like a 1, so it has no problem with that. So here we have the LCM as 3xn squared plus 1. When I divide that, we get this divided by a 1, we get itself times xn. So this is xn into 3xn squared plus a 1, and we are subtracting this 1 divided by this, we get a 1, and then we have 1 into xn cubed plus xn minus 1. Many candidates have a challenge with speed. So when you reach here, always move close with your algebra. Speed is good, but it's not very good. I believe you understand. So xn plus 1, expand this, that will be 3 xn cubed plus xn. This negative 1 distributing inside, we have negative xn cubed minus xn plus a 1. The whole of this we divide by 3xn squared plus a 1. So xn plus 1 is going to give us, so when I get this minus that, I'll be getting 2xn cubed, and this one and this term will cancel out. So we have here plus 1 over 3 xn squared plus 1. This is for n equal to 0, 1, 2, 3. So this is how best you can simplify this, and that is the answer for that. So we have derived. So we have example part B of number 1. So this function already we have f of x this side, so our interest is to simply write the function. This is f of this plus this. So we differentiate, obtain the derivative. When you differentiate the exponent of of x. First of all, when you are differentiating exponents, if I have f of x equals to exponent of, say, any function, say g of x, what you do is you drop the derivative of this times the the exponent of that. So that is the rule for differentiating the exponential functions. So when I differentiate x here, I get 1 times the exponent itself. It will just be this. When I differentiate x, I get a 1. So we substitute xn in f, and that will be exponent of xn. We are simply putting, where there is x, we put xn. So this is xn minus 1. The derivative the same, which is exponent of xn plus a 1. Then quote the Newton-Raphson formula given by xn plus 1 is equal to xn minus f of xn over this, and that is for n 0, 1, like that. So xn plus 1 is given by xn minus, so f of xn is given by exponent of xn plus xn minus 1 divided by exponent of xn plus 1. So this is the Newton-Raphson formula based on Newton-Raphson, and we can simplify. So if I am to simplify, I believe we can take the LCM, and that is exponent of xn plus 1. So if I get this divided by a 1, I get this very function times that, which is xn into exponent of xn plus a 1 minus, if I get this divided by this, I get a 1 times that. We are going to get exponent of xn plus xn minus a 1. So from here we can simplify. So when you simplify, the first term, expand xn plus 1 is going to be xn exponent of xn plus xn. We are trying to now expand this negative, so we're going to have negative exponent of xn, then minus xn, negative and negative 1 here, we're going to have plus 1. All of this we are dividing by exponent of xn plus a 1, and our xn plus 1, when we simplify, here this xn and this xn cancels, so we simply have xn times that minus exponent of xn plus 1. The whole of this over exponent of xn plus 1, and I can maybe leave the function there, or I can simply factorize out the exponent of xn, so I will simply have xn minus 1. Here there is a coefficient of xn and here negative 1, so I can have this, then times exponent of xn plus 1. The whole of this over exponent of xn plus a 1. This is for n equals to 0, 1, 2, and so forth. So that is how we can derive that formula for finding the root of that. So for this case, we are going to have we're going to work out part C, but when you look at this here, there is no 0. So in the third place, to put this in the form f of x equals to 0, so we can bring this here. So we're going to have sine of x minus 2 cos of x equals to 0. So this is now f of x equals to 0. Now we can say let f of x be equivalent to sine of x minus 2 cos of x. Even if you came with this one and then you put this side, still it is okay. Okay, now we obtain the third derivative. Obtain the third derivative, immediately you write the function, and this one will give me, when I differentiate sine of x, I get positive cosine of x. So this is cos of x minus 2. When I differentiate cosine of x, I get what? It is negative sine of x. So this is negative sine of x, and when I try to simplify this, I simply get cos of x, I get plus sine of x. Then substitute the xn, and that will be sine of xn minus 2 cos of xn, further derivative, and that will be cos of xn plus 2 sine of xn. So now we quote the formula, which is xn. We now quote the Newton-Raphson formula that we derived, which is xn minus f of xn, the whole of this divided by the further derivative of xn. So let us just feed the functions here, and that will be xn minus, so this will be sine of xn minus 2 cos of xn divided by cos of xn plus 2 sine of xn. So if we want, we can simplify this by taking the LCM. So xn plus 1 is going to be, the LCM is cos of xn plus 2 sine of xn. When I pick this and divide by 1, that is a simple denominator here, we are simply going to get we are going to get this. So we multiply by the numerator, so we have xn into cos of xn plus 2 sine of xn. Then we subtract. When I get this and divide by that, we get a 1. So we are going to simply have here sine of xn, and then we subtract 2 cos of xn. Let us try to simplify. So this will give us, this xn distributes, so that will be xn plus 2xn sine of xn minus, this is going to be sine of xn, then minus 2 cos of xn. So this is what we have from that, and we divide this by cos of xn plus 2 sine of xn. So if you feel is comfortable, we can group some of these things here. For instance, this one and the cos, you can have this as xn minus 2, then cos of xn plus this and that, we have 2, we have sine of xn, which is common, so I can have 2xn minus 1, then times sine of xn. The whole of this I can divide by cos of xn plus 2 sine of xn. So that can be the formula for finding the Newton-Raphson formula. Someone can simplify and put it to another form by dividing through by a cos. So when you divide through by a cos, you are going to simply get xn plus 1. I see when you divide a cos here, you are going to simply get xn minus 2. This will be just 1. We are dividing cos throughout. Then plus 2xn minus 1. Then this will become a tan of xn. And we divide this by, when you divide here, cos is a 1 plus 2 tan of xn. So watch, at some time, someone can just ask you to derive and help show that it is given by this. So for today, let's end it there. We meet next time with some examples. You can do the exercise which we wrote the answer. Okay.